In this video, I am going to give you a very brief introduction to null space and range. Let's say we have V and W. These are two subspaces. Basically, they're two vector spaces. And T is a linear transformation that goes from vector space V to a vector space W. So in other words, T takes vectors, like this little v, in vector space V, and then transforms it or maps it to a vector W in vector space W. Then the null space of T, denoted null T, is the subset of V. So it's the subset of V given by V is in V and T of V is equal to 0. So here I have a drawing. So in W, I have a 0 vector. Remember, in order to be a vector space, the subspace needs to have an additive identity or a 0. And the null space are all the things in V that are then mapped to the 0. So in my drawing, I have V1 is mapped to 0, V2 is mapped to 0, V3 is mapped to 0. This V over here is mapped to this W. So it is not mapped to 0. So all the blue vectors, though, are my null space. Actually, it's these vectors, V1, V2, and V3. And here I have a drawing illustrating range. Range are all the W's in my vector space W such that W is equal to T of V for some V in V. So here I have W1, W2, W3. So W1 is equal to T of V1 and T of V2. So W1 is in the range. W2 doesn't have anything mapping to it. So W2 is not in the range if I've drawn my entire mapping of T. So if this is my entire mapping of T, then W2 is not in the range. W3 has V3 mapped to it, so W3 is in the range. And again, it's much like domain and range that you learned in algebra a long time ago. So range are the things that gets hit by the transformation. And the way I like to think of this null space, just to add some drama, is the null space are all the vectors in V that get crushed down into this single 0 vector. And actually, this very dramatic phrasing of it also should tell you that the null space gives you a lot of information about this transformation, among other things like how crushing it can be. And before I do some examples, there is this sort of remarkable theorem that says the rank of T, and the rank is the dimension of the range, plus the nullity of T, and the nullity is the dimension of the null space, is equal to n, which is the dimension of your vector space. For our first example, let's say we have a transformation f that goes from R3 to R2. So it takes vectors that look like x1, x2, x3, and it produces this two-dimensional vector here. We want to describe the null space and the range of f, and then we're going to determine the rank and nullity of f. To start, I want a matrix representation of my transformation f. And to get a matrix representation, I want to see how f transforms a basis of R3. So remember from a previous video when we talked about linear transformations, once we know how f transforms a basis, we know how it transforms any vector. So in particular, my matrix A is going to be f on my first basis vector for R3, 1, 0, 0. My second column will be f on my second basis, 0, 1, 0. And my last column will be f on my last basis vector for R3, 0, 0, 1. So I can plug in 1, 0, 0 into my transformation. So x1 minus x2, that's 1 minus 0, gives me 1. And then for my second coordinate, it's x2 plus x3, which is 0 plus 0. So for my 0, 1, 0, when I plug this into my transformation, 0 minus x minus 1 gives me minus 1. x2 plus x3 is 1 plus 0, which is 1. For my third basis vector, x1 minus x2 is 0 minus 0, which is 0, and x2 plus x3 will give me 1. So here is my matrix form of this transformation f. For my null space, I want to know what vectors x get crushed down to 0, 0, my 0 vector in R2. So I know how to solve this. I have my augmented matrix, first my coefficient matrix, and then my solution vector. And this gives me, let me just note this, it gives me, well, reading from the bottom, x2 plus x3 equals 0. In other words, x2 is equal to minus x3, and x1 minus x2 is equal to 0. Yes, which tells me that x1 is equal to minus x2, which tells me these x vectors that get crushed down to 0, 0 are of the form x1 minus x1 and x1. Again, we have x1, x2 is equal to minus x1, and x3 is equal to minus x2, which is the same thing as x1. x3 is equals x1. So this can be written as 1, negative 1, 1, x1. So 1, negative 1, 1 is a basis for the null space, which means the nullity is equal to 1. Again, the nullity is the dimension of the null space. Since it only takes one vector to form a basis for the null space, dimension is equal to 1 and nullity is equal to 1. Using this formula here, that means the rank is equal to, well, we started out with 3 dimensions minus 1 for the nullity, rank is equal to 2. For our next example, let's look at the transformation from R2 now to R3. We are going to describe the null space and the range. We are going to start by finding the matrix representation of T. So we're going to take our first basis vector, which is 1, 0, and our second basis vector, 0, 1, plug it into our transformation. So T of 1, 0, so 0, the x2 is 0, x1 is equal to 1, so we have 1 minus 1, 2. T of E2, so x1 is 0, x2 is 1, that'll give us 2, 1, negative 1. So our matrix that represents this transformation T is 1, negative 1, 2, 2, 1, negative 1. Since last example we focused on the null space, in this example we're going to focus on the range. And the range are the y1, y2, y3, the vectors in R3 that have some vector in R2 that gets mapped on by this transformation. So what vectors, y1, y2, will get mapped? Well, we can solve that, again, using our augmented matrix, our coefficient matrix, plus our solution. And what we get is this matrix then is equivalent, row equivalent to this last matrix here, which is 1, 2, y1, 0, 3, y1 plus y2, and 0, 0 minus y1 plus 5/3 y2 plus y3. Looking at this last condition, that tells us 0 is equal to minus 1/3 y1 plus 5/3 y2 plus y3. So the range of A takes the form y1, y2, and then y3 is equal to 1/3 y1 minus 5/3 y2. Separating out my y1 from my y2, in the first coordinate we have 1 times y1. The second coordinate, there are no factors of y1, so it's 0. And the last coordinate is 1/3 times y1. Plus, and then looking at y2, no factors of y2 in the first coordinate, 1 times y2 in the second coordinate, and minus 5/3 times y2 in the last coordinate. So our solutions are y1, y2, y3 equal to our transformation times some vector in x2 have this form. It's a linear combination of the vectors 1, 0, 1/3 and 0, 1 minus 5/3, which implies 1, 0, 1/3, 0, 1 minus 5/3 is a basis. So I've written that here. 1, 0, 1/3 and 0, 1 minus 5/3 is a basis for the range. Since it takes 2 vectors to form a basis for the range, that means the rank or dimension of the range is equal to 2, which means the nullity is equal to, well, we start off in R2, and then the rank is R2, so the nullity must be 0. So the null space is simply 0. The 0 vector gets mapped to the 0 vector and nothing else. I have one more example which I will go through a little more quickly. We have a transformation from R3, in other words x1, x2, x3, to R2. So we have these 2 coordinates. Find a matrix A such that T of x is equal to AX, and find the rank and nullity of T. To find the matrix representing the transformation, I need to know what the transformation does to the bases 1, 0, 0, 0, 1, 0, and 0, 0, 1. And I get these three vectors, which I make my column vectors of my transformation matrix. So I have 1, 0, negative 1, 1, and 0, minus 1. To find the null of A, I want to know what vectors x get crushed down to the 0. So I take my augmented matrix, my matrix of coefficients A, and then I have my solution, which is the 0 vector, and R2, the 0 vector, is 0, 0. And this is already in row echelon form, so I have my x1, x2, x3, and I get that x2 is equal to x3, and here I get that x1 is equal to x2. So my null space looks like, well, x1 is equal to x2 is equal to x3. It looks like x1, x1, x1. So 1, 1, 1 is a basis for the null space. And since there only takes one vector to make a basis, that means the nullity or the dimension of the null space is equal to 1, which must mean that the rank, we started off with n equals 3, is equal to 2. To review what we have done in this video, we looked at null space and range. So if we have a vector space V and a vector space W, and T is a transformation from V to W, and it's a linear transformation, the null space of T, which we denote null of T, is a subspace of V, that's where we're coming from, given by V is in V and T of V is equal to 0. So in other words, it's the vectors in V that get crushed down into the single vector 0. The range of T is a subset of W, that's where we end up, defined by W is in W and W is equal to T of V for some V. So it's kind of what you normally think of range. It's what ends up things in V get mapped to. That's the range. And we have this other useful theorem, unexpected theorem, remarkable theorem, the rank of T, and the rank is the dimension of the range. And remember, dimension is the number of bases vector, plus the nullity of T, and nullity is the dimension of the null space, is equal to n. And n is, where do we talk about this? N is the dimension of V. And we did 3 examples. This one was the last example. So that's it for this video. Thank you for watching.